Consider our character string, Cavalier, King Charles, Spaniel. Now, you and I both know that those characters, as we see them, are not stored internally inside the computer. Rather, a series of positive and negative pulses are stored. Electromagnetic pulses that are evaluated as binary or base 2 numbers. The negative pulse being a 0 and the positive pulse being the 1. And given the binary number system, we can take a group of these signals, these bits, and derive various numbers from them. Now, your computer has internal codes, EBCDIC or ASCII codes that it uses to interpret a pattern of positive and negatives to be a specific number and therefore a specific character. Show you what I mean. Here we have the ASCII character code table. Now, the ASCII, American Standard Code for Information Interchange, is a set of rules that computer manufacturers follow on how to store different characters in memory. What values or combinations of 0 and 1 will represent whatever you want to store. So, if we take a look at this table, I want to point out 3 columns to you. The leftmost column is labeled DEC. That is the base 10 or decimal number, the ones that you and I are most familiar with. Go over 3 columns to the right and you'll see bin. That's the binary number or base 2 number, and that resembles most closely what your character looks like in your computer's memory. You have to translate the zeros to off bits and the ones to on bits, or negative and positive electromagnetic impulses, to really see what it looks like, but we'll stick with the zeros and ones. Then the last column is the description. And so if we take a look at our first row, a decimal 0, binary value 0 is the null character. It represents nothingness. Now, let's find a capital C. So let's move down. And you notice we have all kinds of special symbols, the Arabic digits, more special symbols, and here are our capital letters. And I'm going to move C to the top, and its ASCII value is 67 in base 10, or 01, 00, 00, 11 in binary, but that's too hard to say. So I'm going to call it 67, my capital or uppercase C, which is not the same thing as a lowercase c. We have to move on to find that value. It's there. It's 99, lowercase c. Or, if I must, the binary 011, 00011. 99 means more to me. So we'll call it 99. Now, everything that you can store in memory has an ASCII value. Even a carriage return or a bell ringing. They all have their various ASCII values. So now we know a little bit more about how characters are stored in memory. So, I'm back in my JavaScript, and I'm looking at the charCodeAt method. The charCodeAt looks at a specific character and returns its code. So, I'm going to find the character code of the first character in our phrase, Cavalier, King Charles Spaniel. Now we all know it's a C, but what's its code? So this line shows us how to get at it. It's txt, that's the name of our variable that holds our phrase, dot charCodeAt method, and then the parameter is the index of the character I'm after. So in this case, I should get the ASCII code for a capital C. Now, in this next example, I'm going to go after the code at 15, which, if you remember, is our lowercase h. And then, one more time, I'm going to go after the last character. Remember, that's our text.length minus 1 to get the index of the last character in a string. And I'm going to find out what the code is for lowercase l. charCodeAt. That's our method. Okay, we're back where we started, looking at a web page for the charCodeAt method. Our phrase or our variable txt contains Cavalier King Charles Spaniel. We've gone into JavaScript and added our code, so it's time for a test run. Let's refresh our page and see what we get. The first character is 67. That's your uppercase C. Position 15 is the character 104. Now that is your lowercase h. And the last character is a 108, which is the lowercase l. That's all there is to it.